Namaste. I am Paragmoni Kalita from Remote Center 1153. I am going to present the governing equations for one-dimensional steady compressible flow without shaft work and viscous effects. The governing equations for any fluid flow can be categorized into conservation laws for mass, momentum, and energy that are given in integral form by the continuity equation, momentum equation, and energy equation respectively, as shown in this slide. Now, the assumptions for one-dimensional flow case are that the flow should be through a constant area duct. The viscous forces and body forces must be absent. The flow must be steady. There is no shaft work. The change in potential energy is negligible, and the flow properties are constant along any cross-section normal to the streamlines. This means if we concentrate our attention on any cross-section normal to the streamline, such the one shown here, the flow parameters here, at all points along the cross-section normal to the streamlines will be same. Now, to simplify the continuity equation for steady one-dimensional flow, we remove the partial derivative with reference to time that is given by the first term in this equation, and this term, when we simplify for one-dimensional flow, we find that there are only two phases across which flow will take place. The left phase, for which the unit normal vector is given by minus I, and the right phase for which the unit normal vector is given by plus I. And since the flow is one-dimensional, the magnitudes of the areas, that is A1 and A2, they are same, and therefore we get the integral form for steady one-dimensional compressible flow given by this equation, that is rho 1 V1 equal to rho 2 V2. Proceeding in a similar line, we can simplify the momentum equation for one-dimensional flow. Now, this momentum equation is derived from the second law of motion proposed by Newton, and accordingly here the rate of change of momentum is equal to the net external force applied on this. The external forces for inviscid flow are given by the pressure force and the body force, because the viscous force is absent. Even for compressible flow, we can ignore the body force term, and because the flow is steady, we can remove the partial derivative of time, and we get this equation simplified to surface integral of momentum to the surface integral of the pressure force term. And when we simplify, we get that the impulse function is constant, that is P plus rho V square is constant along the flow. For the energy equation, the basic idea is that energy is conserved. That means the rate of change of energy within a controlled volume is because of the rate of work done on the system and the heat transfer into the system. Now, in this expression for steady flow, the partial derivative with reference to time will vanish, and the body forces are absent, the viscous forces are absent, and accordingly we can simplify the integral form of the energy equation for one-dimensional flow, and we get this form. This here EI represents the internal energy per unit mass of the substance. Further, summation of internal energy and P by rho, that represents the flow work or flow energy, is the enthalpy, and by simplifying here summation of internal energy and flow energy equal to the enthalpy, we get this form of the steady one-dimensional compressible flow energy equation, which says that summation of enthalpy and kinetic energy at inlet plus the heat transfer between inlet and outlet per unit mass is equal to summation of enthalpy and kinetic energy per unit mass at the outlet. Thank you.